Example problem number 8 is another integrated kinematics and dynamics problem. And as a reminder, the one parameter that links kinematics and dynamics together is acceleration. So what we need to do is we need to organize the information in terms of the kinematics information and the dynamics information. So we have a 1,000 kilogram car and it is being pushed with an applied force of 300 newtons. So mass is 1,000 kilograms. And I'm calling this applied force F sub A being applied, and that is 300 newtons. Of course, this would be your dynamics related information. In part A, we're asked to find the acceleration of the car. And again, acceleration can be found either using dynamics or kinematics, but so far we have been given no kinematics information. So the likely approach will be that we are going to be solving this acceleration using the dynamics information. But when we take a look at part B, it's asking how long. Now, how long is a measurement of time, which is a kinematics thing. And we're asked to figure out how long it'll take to accelerate to 108 kilometers per hour from rest. Part B is a dynamics problem, which requires dynamics information. The key takeaways is we know that it accelerates to 108 kilometers per hour from rest, which means our V1 is 0 meters per second, rest, and our V2 is 108 kilometers per hour, which is 30 meters per second when you put it in the proper units. Now let's take a look at part C. In part C, what force? Okay, so now it's gone back to a dynamics problem. What force would be required to stop? Okay, keyword stop the vehicle in 30 meters. Okay, so 30 meters, dynamics information. Stop also implies some dynamics and not dynamics. I apologize. 30 meters is kinematics information, and stop would also be related to some kinematics information from a speed of 108 kilometers per hour. So we're stopping from an initial speed of 108 kilometers per hour. So now when we take a look at what's going on in part C, we now know our initial velocity or initial speed is 30 meters per second, and our final speed is 0 meters per second because of its stopping, and through a distance of 30 meters. And again, these kinematic equations are technically vector related. They can calculate distance and speed, but really the formulas are designed for vectors, so displacement and velocity. But C has two parts. One, we're looking to figure out what the stopping force would be if that 300 Newton force is no longer applied, the applied force in part A and B. And then we're going to do it again when that 300 Newton force is still being applied. So there are two possible ways that we could answer this, and we're going to work with both. So starting off with part A, we know it's going to be a dynamics problem because we don't have any kinematics information to start off with. The formulas we'll likely be using, F net equals ma, Fg equals mg. Didn't make any mention to the force of friction per se. So the force of friction formula is likely not relevant in this case. And we, of course, have our a couple of kinematic formulas listed over here, and you'll see why we're going to be using those momentarily. So for part A, we're looking for the acceleration. And again, as a reminder, acceleration is both a dynamics thing and a kinematics thing. And since it made no mention of friction, we can just focus on the X components because the Y component simply cancels out. Obviously, this question is a little less realistic because in real life, we would have friction, but I digress. So again, the normal force and the force of gravity will cancel each other out in this case because the vehicle is not going to be floating or sinking. All the acceleration is going to be happening on the X component, nothing in the Y. So the two Y forces cancel each other out. The only relevant force at the moment would be the applied force along the X axis. So since the Y component is 0, that means the acceleration in the X is just the acceleration. Focusing on F net X is equal to FA. FA is the only real force acting on the system along the X axis. Thanks to Newton's second law, we know that F net is equal to mass times acceleration. And the reason why we don't have a subscript X is because AX equals A in this case. FA is positive because it's in the forward direction. Isolating for acceleration by removing the M's attached through multiplication. Opposite of multiplication is division. So we end up getting positive 300 divided by 1,000, or positive 0.3000 meters per second squared, or 0.3000 meters per second squared in the forward direction. So that is the acceleration of our vehicle with this applied force and that mass. As you can see, it's not a very robust rate of acceleration. It's pretty slow. Part B, we're looking for the time. And since time is a kinematics thing, I should say, we're going to take a look at our list of kinematic parameters. So here's what was given. We know that the original velocity was 0. The original speed, I guess, was 0 meters per second. It accelerated up to 30 meters per second. We determined that the acceleration was 0.3 meters per second squared. And let me put a couple of positive signs in here. Of course, I've given it the amber check mark because since it is a calculated result, it is subject to error. Now, technically, if this was grade 12, I would make you, instead of using the 0.3, I would have you substitute this expression in. Okay, so that is really the best way to do it in terms of getting the best result with the least chance of error. However, it does get cumbersome sometimes. So in the interest of expediency, we're just going to work with the actual value this time. And since there were no ugly decimal numbers, we will get the same result regardless. Well, as you can see, we're looking for time and we don't have our distance/displacement. So the relevant formula, of course, would be the one formula, or there's actually technically two formulas that we could use that do not have distance in it. I chose to use equation number 6 as opposed to equation number 7. In this case, this is V2 is equal to V1 plus AT. We are isolating for time, so we have to use SAMDEB, of course, this being our term of concern. Removing this term via subtraction. Next step, of course, we have to remove this factor from time, and using the opposite of multiplication is division. So we get time is equal to V2 minus V1 over A. Substituting our values in, we get 30 minus 0, final minus initial divided by 0.3, and we get a time of 100 seconds. And we should really write that with 4 sig figs. Now, moving on to part C, the situation has changed. So the acceleration that we just calculated and the time that we calculated, so this value here and this value here is no longer applicable. And that's because we've changed the situation. We're now applying brakes and causing the vehicle to stop. So that being said, this is a dynamics problem that requires kinematics to solve. We are solving for this stopping force, which, really is just code for the force of friction. So here's our free body diagram. We have the stopping force in the x-axis, the normal force, and the force of gravity. In this version 1, we're assuming that 300 newtons in the forward direction is shut off. Again, since we're not requiring the force of friction formula, that is, force of friction is equal to mu Fn. Since we don't need to figure out the Fn, we actually don't have to worry about the y component. The x component is all that is relevant in this particular case. So to find Fs, we know that F net x is equal to our Fs. Now, here's the tricky little bit, and this note is something to pay attention to. So here is how I have set up this question. Notice I didn't put a plus or minus in front of F net. I just left it as MA, but I put a negative sign in front of the stopping force. I did that for a reason. We know that it's in the negative direction. So what this means by doing this, and this is very important, Fs is no longer a vector. Fs is just a magnitude because the direction is here. We've already made it negative. By setting it up this way, Fs will actually not give us a negative number. We will get a positive number. But notice I made no decision about here. I didn't put a negative sign in front of here. So this is kind of a little tricky nuance thing I did here. Here, I extracted the direction. But since I didn't put anything out in front here, A is still positive or a negative value. This is actually still a vector, technically. And its direction is built inside of the A, where here I extracted it out. So Fs is just a magnitude where the direction is out front. In this question, I'm allowing the algebra to take care of it. So we know that the left side has to be negative, but when you see the math, it'll turn out that the acceleration actually is going to be a negative number. So there's a number of ways that we could have done this. We could have also said, hey, I know that that's negative, and then we just would have been working totally in magnitudes, but it gets confusing. So I left it as MA equals negative Fs. If we do this right, the value for Fs should not come out negative because we've already pulled that out. It should be just the magnitude. Now, in order to get Fs, we have the mass, but we need to figure out what the acceleration is. Now, of course, the acceleration, that is also a kinematics thing. So we're going to do a little aside to calculate our value for the acceleration. Well, here's what we know. We knew that the vehicle stopped in 30 meters. with an initial speed of, or initial velocity, I guess, of positive 30 meters per second and comes to a stop. We're looking for the acceleration, of course. So these are all positive values. So that works out to our equation number 5. And of course, we're isolating for acceleration using SAMDEB. So step 1, we isolate our term of concern, which is this last one here. Bringing the V1 squared to the other side makes it subtraction. And then, of course, we need to extract the 2 and the D from A, and those are attached through multiplication. The opposite of multiplication is division. So A is equal to V2 squared minus V1 squared over 2D. And again, in grade 12, I'd make you actually substitute this in for the A and not the actual value. But again, in the interest of expediency, we'll just calculate our value for our acceleration. And since it works out to a nice non-rounded number of negative 15, here, let's go back to the yellow, negative 15 meters per second squared, we don't have any rounding issues to be concerned with. So hopefully we still get a non-negative answer. Well, negative times 1,000 times negative 15, and there we go, 15,000 newtons. That's just the magnitude of the stopping force, but we know that the stopping force is negative in the backwards direction. So therefore, when we state the final answer, we have to interpret it based on the diagram and the fact that we made it negative here. We already made it negative up there. And that's why the answer came out as a non-negative number. Now, in part 2 of this, we're assuming that this FA is still active. That makes our x-axis have a little bit more complexity. Again, the y-axis is irrelevant in this case because they just cancel each other out and all the acceleration is happening along the x. So to find Fs in this case, we've got F net x is equal to Fa plus Fs. But when we drop the vector notation, I made no decision for the direction of MA. I'm just letting the algebra take care of its direction. But here I pulled out a positive sign because I know FA is in the positive direction. And of course, the subtraction means backwards. Isolating for Fs, again using SAMDEB, 1, 2, 3 terms. Fs is my term of concern. Since it's negative, I'm going to bring it over to the left-hand side, making it positive. And at the same time, I'm going to bring the MA term over to the right-hand side. So I get Fs is equal to Fa minus MA. Once again, since I've already made it negative, this is now, sorry, let's be consistent. This is now just going to be a magnitude. So we should not get a negative number if we did it correctly because we already made it negative here. Substituting our values in, we have Fs is equal to 300 minus 1,000 times negative 15. And of course, a negative and a negative ultimately makes a positive. So we end up getting 15,300 newtons backwards. And again, that's because we know that it is backwards. We already made it backwards. And this should make sense because in the previous example, it was just 15,000 newtons to stop the vehicle when we didn't have an additional push at the front. Now that FA is still pushing with 300 newtons, we have to add another 300. And look at that, a little extra zero there. We have to add a little extra force to compensate for this extra FA. And I should probably put a tilde on this because I think we're working with 4 sig figs. Yep. And there you have it. Negative 15,000. Sorry, my bad. Not negative 15,000. 15,300. Oh dear. Newtons back.